This Camtasia video recording is to demonstrate an example on absorbing states from Markov analysis. An absorbing state is a state that once you've got into it, you can't get out of it. For example, once you've paid your bill will be fully paid. Another example would be, once you've passed your exam, you will always have passed your exam. The probability of going from an absorbing state to any other state is 0. Here is an example. In this example, there are two absorbing states, paid and bad debt. And you can identify absorbing states by the rows which have a single 1 and the remainder of zeros for the probabilities. And you can see this with both paid and bad debt. The other two rows show the non-absorbing states going from a non-absorbing state to a non-absorbing state, or a non-absorbing state to an absorbing state. For example, less than 1 month to fully paid is a non-absorbing state to an absorbing state, and less than 1 month to 1 to 3 months is a non-absorbing state to a non-absorbing state. The first step is to rearrange the matrix to show the absorbing states listed first. The two absorbing states are paid and bad debt. So we move paid to the first row, bad debt to the second row, paid to the first column, and bad debt to the second column. The non-absorbing states, less than 1 month and 1 to 3 months, go in the rows 3 and 4 and columns 3 and 4. We now need to move the probabilities into the new format. So for example, 1 to 3 months goes from 1 to 3 months to bad debt is 0.4. If we go on the new matrix, 1 to 3 months to bad debt is 0.4. So we've transformed the matrix now into the format that we need, with the two absorbing states in the first two rows and first two columns, and we have ones and zeros, a single 1 and zeros for the probabilities on both of these rows. And we've updated the third and fourth column to show the probabilities of going from a non-absorbing state to a non-absorbing state, or from a non-absorbing state to an absorbing state. This new matrix is important because it needs partitioning into 4 parts, comprising of the identity matrix showing 1, 0, 0, 1, the 0 matrix showing 4 zeros, the Q matrix which shows transition from a non-absorbing state to a non-absorbing state, and this further matrix R, which is not labelled, is going from a non-absorbing state to an absorbing state. We need to find I minus Q, and I is the identity matrix, Q is this transition matrix for non-absorbing states, so we have I minus Q gives us I minus Q for each of the cell positions. So 1, 0.1 gives you 1 minus 0.1, 0 minus 0.3 gives you 0 minus 0.3, 0 minus 0 gives us 0 minus 0, and 1 minus 0.2 gives us 1 minus 0.2. We're now going to calculate for each cell the values. So 1 minus 0.1 is 0.9, 0 minus 0.3 is minus 0.3, 0 minus 0 is 0, and 1 minus 0.2 is 0.8. Well, why are we doing this? We're doing it because we need to find the F matrix, which is the inverse of I minus Q. The formula for an inverse is this, and so we're going to proceed with using this formula to calculate the inverse of I minus Q. So, looking at the positions in the A matrix, we've got A, B, C, D, which gives us A, B, C, D. So A is 0.9, B is minus 0.3, C is 0, and D is 0.8. We can now find the determinant, which is the 1 over AD minus BC. So we're just going to calculate that little bit first. So here we have 1 over AD minus BC, 1 divided by A is 0.9, D is 0.8, minus B minus 0.3 times 0. And if we calculate that, we get 1.3888. So to find the inverse I minus q to the minus 1, we need to follow the formula as shown here, is of a to the minus 1. We know that the determinant is 1.3888, and we just have to rearrange the cells so that D is shown in the top left position and A moves to the bottom right, and we change the sign on B and C to become negative. So here we have the value for D being 0.8, here we have the value for A being 0.9, B had a value of minus 0.3 and we want D to do minus B, so it's minus 0.3, which gives us plus 0.3. So now we just need to finish finding the inverse of I minus Q by doing the multiplication of 1.388 times the matrix. Now when you're doing a multiplication with a single number and a matrix, you multiply each individual element by that single number. So we have 1.388 times 0.8, 1.388 times plus 0.3, 1.388 times 0, 1.388 times 0.9. So we can now see this matrix multiplication, and if we calculate these values, we get 1.111, 0.4167, 0 and 1.25. Remember to keep to enough decimal places so that your answer is accurate enough. So what does this mean? Well, the inverse of I minus Q, or I minus Q to the minus 1, is the F matrix. Now the F matrix is important because it looks at the absorbing states and how long it will take, the number of time periods for the system to spend in each non-absorbing state before becoming fully absorbed. Just to note that the first two rows now represent the non-absorbing states and the first two columns represent the absorbing states. So we're going to have less than 1 month in arrears, 1 to 3 months in arrears, and then we're going to have paid or bad debt. So if the calculation we've just done says that it takes for less than 1 month in arrears to become fully paid, it takes 1.11 time periods. So again, the number of time periods or months of going from 1 to 3 months in arrears to a bad debt situation is 1.25 months. So now we need to find the FR matrix, which is a matrix multiplication of the F matrix and the R matrix, which I talked about earlier. The R matrix is the matrix going from a non-absorbing state to an absorbing state. So here we have the F matrix, which we'd already calculated, and here we have the R matrix. To do matrix multiplication, we have to multiply the row of the first matrix by the column of the second matrix. If you consider the position that you're in, the first row and the first column gives us the answer in the first row, first column. And what we have to do is multiply the first element by the first element and the second element by the second element. So we have 1.11 multiplied by 0.6 goes here, plus 0.4167 plus 0.4 goes here, and if we calculate that we get 0.88833 recurring. So again, the first row, first column, the answer goes in the position of the first row, first column. So for the first row, second column, we have 1.11 times 0 plus 0.1467 times 0.4, which gives us 0.1667. And if you add the new values of the first row, that should add up to 1 because it shows the probability of going from a non-absorbing state to an absorbing state. And again, we have the bottom row, first column, being 0.5, and the bottom row, second column, being 0.5. So now we have the final solution for FR, and I've put in the labels less than 1 month and 1 to 3 months being the non-absorbing states, going to the absorbing states, paid and bad debt. So what does this mean? It's telling us probabilities from going from a non-absorbing state to an absorbing state. So if we go from less than 1 month in arrears to fully paid, the probability is 0.833. The probability of going from 1 to 3 months in arrears to a bad debt situation is 0.5. So if we wanted to know how many people would go from a non-absorbing state of less than 1 month in arrears or 1 to 3 months in arrears to being fully paid or a bad debt situation, we simply pre-multiply the number of people into the FR matrix, and we do the row by the column again. 1,000 times 0.833, 2,000 times 0.5 goes in the first position, 1,000 times 0.1667, and 2,000 times 0.5 goes in the second column. So if we calculate this, we get out of the position of the non-absorbing state, we get 1,833 who are fully paid, and 1,166 or 67 who end up in a bad debt position.